At least a bit.
I saw Stan coming, and I was like, wait, I could probably stop.
Well, at least I don't know about this.
Wait, did we get the hospital?
Right now.
Oh, this isn't this the note?
Where did you get that? I don't think I got that.
Well,
Yeah, this is the note.
When did you get that?
Did you not get
5
it?
minutes ago?
No, I didn't get that 5 minutes ago.
Oh, did you lower your hand after? Because like it was coming out paper. I just wanted. I told you to raise your hand proud.
You didn't raise it proud. I think I was over there.
That.
I think I was the only one on the other side of the room.
I mean, yeah.
I mean, not being that good.
Yeah. You can sit like right here. Oh, I might. Thank you. Camera, USB. It's on the other side. In this video, you're gonna see me study for PC. Study with me.
Just get to look at your reaction.
Study with me, study buddy. Let's go.
All right, sorry everybody. All right, now I'm ready for real. So here is 7376. Doing 2 segments because they're both pretty manageable. First one is called Euler's method. Don't you mean Euler's method? No, I mean well, this dude spoke German, and that's the German or close to the German pronunciation. Okay, well, but if my name was Martinez, you wouldn't say Martinis because we're in America. Anyway, Euler. So here is what this does. It this. Pretend you had this differential equation. And let me make it kind of complicated so that we don't know how to solve it. I don't know. XY plus 2x cubed minus y. Something like that. Does that work? Yeah, because then we don't know how to solve it. And then, so like I said, we don't know how to solve this, but if for whatever reason I had some initial condition that I knew, actually, let me back up a little bit. I don't know how to solve this, and I don't know what the solution for this would look like, but let's say the solution for that looks something like, I don't know, something like this. I don't know, whatever. Again, I don't actually know what this looks like. This is just for teaching purposes what we're about to do. I don't know this purple. But to show you what we're going to do. Let's say I don't know that purple, but I do know some initial condition like when x is 0, y is whatever. Let's say I did know this point. And let's say for whatever reason, I'm interested in grabbing or like the y value of this point. Let me make that like orange. Then what this method does is we can approximate it with tangent lines, which is something you know what to do or like how to do already. But we do it not with a single tangent line, but with a bunch of tangent lines. But
There known value have to be a 0.
no, it could be anywhere. But
So any known value.
yeah, any known value. You start here and you want to get a point over here, that's possible. You start here and you want to get a point over here, that's possible. But here's how you do it: is at the known value, you use the tangent line. There's the tangent line. But then instead of using this tangent line, this green tangent line to approximate this orange point, because that would be pretty far off. You don't have to make it go this far, but just to show you how far off that would be way over here where you want the point right there. That would be not a very good approximation. So instead of using that same tangent line to approximate all the way over here, what you do is you approximate a point pretty close so that it's not too far off from the purple. So instead you approximate this point instead of this purple point using that tangent line. Then you say, okay, I know that'll be kind of close to the purple. Let me pretend it's exactly on the purple. Then you then you get a tangent line from here, pretending it's right on the line. That would be something like this. And you approximate this point instead of this point. And then from there, you get another tangent line. You approximate this point instead of that point. And then you get a tangent line from there. And then finally you get this point instead of this point. So you get a closer approximation. So if that was too much, all I'm saying is you're going to have a known value. You use a bunch of tangent lines in as many steps as you want, as many steps as you get asked, and use that many tangent lines to approximate that point that you're interested in. That's what's coming up. Questions?
Is there a way to do it like an infinite amount of times? You just get the actual.
Oh wow, what a question!
Yeah, like if we did the same thing that we did to find together. The limit has the number of steps.
Yeah.
Or you close to the actual.
But there's so many variables that I don't see how. The question for the video was, can you do this an infinite number? Like, can you take the limit of this an infinite number of times and get an approximation of like the exact value? And I've never seen that, but that's a good idea. But I think there's too many moving parts. There's too many variables in that. Like the x coordinate, the y coordinate, and the slope are all are all like variables that you don't know. Like it'd be too difficult to do. But that's my initial thought, just because I've never seen this. I've never thought about that. But maybe there's.
I mean, given that you could, would that give you the actual?
That sounds intuitively the first, like off the top of my head. Yes, that sounds right.
Would that we cancel it some out if you're like playing with the random? That just gets the parent motion.
Yeah.
So, but what do you actually do with it? You just get this dy dx.
Well, I limit of derivative is not an integral. But I see what you're saying. If you did something enough times and you're accumulating it over time. Yeah, I don't know. Let me think about that. But let me get to the lesson because I got 2 sections to cover. But yeah, let me think about that later. Good job, y'all. Yeah. Okay. So this is a repetitive thing, like April's saying. Here's how other teachers like to teach this: is with this little chart where you fill it out and then you like add this plus this, and then that'll get you the next point and whatever. But I actually never learned with this chart because to me it makes more sense to know what I'm doing rather than memorize this chart. So I'm going to teach you to do 7,000 tangent lines. But if you're interested in, let me just learn this little shortcut chart, then look that up on the internet. Because for real, I don't know really how this is used. I could try to figure it out, but I just don't see the need. So anyway, interested in this, look it up on YouTube. I bet everybody teaches it this way. But I think it's more helpful to actually do the tangent. So here's like one example. It says, here's the differential equation. And I know that it passes through 0.5 to find an approximation for 0.8 using Euler's method. With 2 equal steps. Look at 2 equal steps instead. Okay, so the idea is I start at 0 and I'm interested in 0.8 and I want to get there in 2 steps, then how wide should each step be? 0.4. Okay, right. So I'm going to get an approximation up to 0.4, then I'm going to use that to get to up to 0.8. So here's my 2 steps. Whoop, whoop, like that. Okay, and so let's do it, like I said, the long way, like I like to do it. So tangent line 1 would look something like y minus something equals something times something. Then again, your tangent line is going to be at the point that you were given. So 0, 5. So 0, 5, boom. And then the slope, you tell me how to get the slope actually.
X value is dy.
Nice. Yeah, so here's your dy dx. Plug in your x value. In this case, it's just x. Sometimes you might see x and y, in which case you plug in both. So here you're getting slope. Dx equals 0 minus 2, which would be -2. Cool. Okay, so there's my slope. Put that into here. And then I use this tangent line to approximate my next step. which my next step, remember what we said was 0. So what? -2 times 0.4 minus 0. I guess I didn't right minus 0, but then plus 5, which is -0.8 plus 5, which is 4.2. So now my in-between approximation, my approximation for this point would be this new point, which is 0.4 on the x and 4.2 for y. And then, like I said, you treat this as if this was on the function, and you get a new tangent line from here, and that will get you to the 0 point. So, okay, second tangent line. Let me be right back. I'll get that for the board. I was gonna say that up here, probably gonna be. And so if you have trouble mapping it over, that'll give you. All right, tangent line 2, here it is. 5 minus 4.2 equals some slope times x minus 0.4 with my others. Then again, get the slope from here. So slope would be this. 0.4 minus 2 is -1.6. There's my slope. There's that. I use this to approximate my next step, which is my end goal in this case, 0.8. Y equals -1.6 times 0.8 minus 0.4 plus the 4.2. And if you're not trying to do 1.6 times 0.4, that's
-1.
what?
Wait, am I crazy? Yeah. Yeah. Wait. Oh, wait, I forgot the minus 0.4. Oh my god. Never mind.
Well, now I'm confused, but my final answer was 3.52.
I got it.
Okay, all right. That's pretty cool. So then that would be, okay, you could circle this, but just to fully formalize it, I would say that y of 0.8 is about equal to 3.5.
I think look at the grandson of the thing you're both.
Yeah, I know. I thought about that. All right. Next one. Actually, the next several are the same thing. So let me just say one thing about the next one, and then I think you can handle it from there. So it says, here's a differential equation again. Notice now it has x's and y's. And it says, if y is 3 when x is 2, use Euler's method with 3 equal steps to approximate y when x is 3.5. Okay, so yeah, very tedious. That is the sound that I make when I get asked about this too. But hopefully it's not super hard. It's very tedious. But okay, 3 equal steps to get from, what is it? From 2 to 3.5. So how wide should each step be? Next, okay. So I'm going to go from here to 2.5, 2.5 to 3, and then 3 to 3.5. Those are my 3 steps. Woo. Okay. So then, okay, let's do it. Let's get into it. Here's my first tangent line. Y minus 3 equals something times x minus 2. So I see you guys all working ahead. So I'll go fast through this. Plug in your x and y, dy dx equals 2 times 2 minus 3. Which is 4 minus 3, which is 1. So here's my slope of 1. Approximate your next step, which would be y equals 1 times x minus 3. And then let me just make sure you guys did the right thing. What you put here for the x word? Oh, 2.5, good job. Yeah, because now we're not starting at 0, so don't put 0.5, even though that's the step size. We're going up to 2. All right, that's what I wanted to check. So then feel free to work ahead. I'll put the answer up here, and then you guys can check when you're ready. Yeah, I mean, sometimes on the AP test, no. Yeah. And your name is on the pass of the library. If you could. Cool, thank you, good job. Okay. Oh. What's it?
1.05.
Yeah. Or 5. And then if you calculate this, I got 5.125. That's your approximation. Because you got to the 3.5. Okay, you do a weird stuff. Oh, yeah. Questions, or are you guys good? Anybody? Yeah, okay. Like I said, it's tedious and there's so many chances to mess up. So like take your time and whatever, but it shouldn't be super hard. It's just like a lot of things to keep track of. What's up? What's your song of the day? Song of the day? I'll let me think about it after. Okay. And then next one is the same thing, only you get a chart. So actually this one is a little bit easier. So it says do it in 2 steps and use the little chart.
There's a better way of trying that.
Maybe, I mean, this little chart saves you from writing all the tangent lines. But it's like you got to keep track of like what's the delta x. This is like step size. This is the slope at that point. This is it's just organizing the work differently. But I don't think it saves you time.
Like how we have a formula for like.
I think it's just like this is just constructing the whole entire formula that we are doing, but in a different way.
Yeah, exactly. So short answer is I've never seen a formula that you can memorize and do. Like this is the closest thing I've seen to a formula. But you'll notice it's still doing the same amount of work. just put it is just organized. Like this is evaluate the derivative. That's us doing that. Now take the delta y and then how much did delta go up? So that's slope times step. Here somewhere. So I don't know a quicker, easier way, but maybe there's. All right, this one is the same thing with a chart, and I'm afraid on time. So, well, actually, I think we have time. We have time. So even if you don't want to do it, just do it real quick. It's a 2-step thing, and it tells you the steps. So let's do it real quick. End line point y minus y1 2 equals slope bf prime times x minus x1. Good. So that means that y equals 0.4 times. What was my next step? Oh yeah, 2.8 minus 3 plus 2. And if you calculate that, you'll get 1.92. So your new point is 2.8. And now end in line 2. That's minus 0.8. So this one's kind of nice because it does the slope for you. Okay, and then you solve this. So y, you plug in the 2.6, 2.7, 2.6 minus 2.8 plus the 1.92. And if you calculate that, you end up with, I got 1.78. Boom. Didn't hear any of that. Oh. Maybe I rounded. No, I didn't.
I got some.
Oh, nice. All right, cool. So we're smiling. Hopefully that makes sense. Keep that in your brain because they tend to like this on the AP test. Like I've seen it on there, like every year it's on there, but sometimes it's on there like twice or 3 times. So some free points if you know this. Okay, and 7.6 is about logistic models, which we did not talk about in AB, obviously, but it's similar to something we've talked about in AB. Let me give you a quick, like, this is all you need to know, and then let me say a lot of stuff about it. So all you need to know in terms of the AP test from about logistic functions or differential equations is that they look like this. This is the logistic differential equation. It looks like ky times L minus y. We'll talk about y in a second. But this is basically all you need to know. And you need to know that L is what's called a carrying capacity or a limiting factor. And you need to know what it says down there, but we'll get to it once I explain it. But just to like let you guys like relax so that you don't feel like, oh, I need to know all this stuff. No, this is basically all you need to know. So watch this. What this says up here in this paragraph, I think it does a good job of explaining that we've talked about in class how populations grow exponentially and things like that. But that's kind of true up to a point, because if population grew exponentially forever, like the Earth wouldn't be able to sustain it. So at some point you like run out of space or run out of shelter or run out of food or whatever, and it starts to level off. And that's true for a lot of things. Like it gives another example down here. So they grow exponentially up to a point, and then it has to start leveling off. And this shape is what the logistic curve looks like. So let me read this and make sure I didn't want to say anything else. Many things in this good thing, population. After a while, yeah, this is what I was saying. Oh, okay. And so we talked about how for exponential growth, like population, the more people that are there, the more that the population can spread. So that's the rate of change growth is directly proportional to the population itself. That's for exponential growth. But if you're talking about logistic growth, then yes, the more people you have, the faster the population can spread. But the closer you get to this carrying capacity where like the earth can't sustain anymore, then it'll start slowing down a little more. So what this says in bold over here is that it's proportional to the current value and how far the current value is from the limiting capacity or the carrying capacity. That's why you'll see that in the differential equation.
No problem with one of these.
No, not. I don't think so.
It had like a limit on top. Yeah.
Yeah, because like,
It had below and a
was-
bottom.
like the milk wouldn't get any hotter once it reached the temperature of the water around it.
I think it was straight up exponential because you wouldn't be able to solve it otherwise. And I looked into the graph and I was like, oh yeah, of course it makes sense why this equation looked like that. So I'll talk to you about that later. Because you asked, wait, wouldn't this not look like that? And I was like, oh yeah, wait, it would, but it would because it's double reverse. But anyway, I'll talk about that later. The milk problem. Let me pull that up later. But no, it did not look exactly like this. It looked more. It looked more exponential. It didn't have this part. All right. Anyway, the example that it gives for this is, so we just talked about population, but here's another fun example is it says, imagine that a rumor is spreading throughout a school of 2,000 students. Then the rate at which the rumor is spread is proportional to both the number of students who have heard it and the new number of students who haven't heard it yet. Logistic curve. Okay, and then it shows a picture of this. But like intuitively, if only one person has heard the rumor and he tells 3 people, and those 3 people each tell 3 people, and so on, then it starts to grow really, really fast, really quick. But then, as more and more people hear it, like as the whole school population begins to hear it, then there's fewer people to tell. So like you start to tell somebody, and they're like, "No, I've already heard that rumor." So that's why it slows down, and approaches the 2,000 students who go to the school. With that makes sense. Yeah. All right, cool. And then here, like again, like I said, this is the summary of everything you need to know for this section. So, logistic differential equations look like this. What you'll get asked on the test is either something like, what is the carrying capacity? Or when was it growing fastest? And these logistic curves will grow fastest right when it gets to about exactly halfway to the carrying capacity. And you can kind of think about why that is in terms of like, as this gets big and as this gets big, when would it be biggest? I'll let you think about that because it's kind of easy to convince yourself that that's true. But that's what this part says down here. Has the greatest rate of change when y is L/2. Cool. All right. And then one last thing that I should say. I think the last thing that I want to say about this is that sometimes you have it written like this, and other times you'll see it with the L factored out so that this becomes a 1. Just I guess people like to see a 1 right there. But you'll see it both ways, but and then both of these are equivalent. You just have to recognize that, like, if there's a y in here and a 1 minus y in here, or a number minus y, that's logistic. Okay, so here's some examples of what you'll get asked, and you'll see, like, if I gave this to you in Algebra 1, you would have been like, this is no problem, like, I can answer it. So hopefully not a big deal now in calculus. It says, the rate at which a flu spreads through a community is modeled by a logistic differential equation that where t is measured in days and t is greater than 0. Okay, so how many people had the flu at the time when it was spreading the fastest? So what is it? Yeah, 1,500, because the limiting capacity or the carrying capacity is 3,000. So half of that would be 1,500. So 1,500. Yeah, I'm just going to 1,500, but I got that from dividing this by.
Say 3,000 divided by 2.
Yeah, exactly. I didn't even know.
Ratio.
Yeah. Okay. And then it says, it asks a similar thing in a different way. It says, what was the rate of change when the spread of the flu sorry, of the spread of the fluid when it was spreading the fastest. So what do I do here? Yeah, plug in 1500 into the derivative, and that's the answer. All right, D P T. It is minus 1500. There you go. And then you can circle that on the test plot if you want to know what number that is. That's 2250. 2,250. And I guess that would be cases of the flu per day. Cases day. Yes.
You have both, like base limit function, or sorry, base log function. If you're trying to find a variable value, like something like other graph like that, you have to, but like it didn't match up exactly with one thing, but you have to find like R and find these. Like how do you model the difference between an actual function and a base logarithmic function?
Oh.
You use R.
Like, would you use the software R? Like,
No, like
program?
R squared.
Oh, yeah, maybe. Yeah, I'm not so good. Like, I didn't take that many applied math classes. So I'm not so sure how like people do that type of stuff. But yeah, there's programs out there that will try to match up your data points to like a logistic curve or whatever. And yeah, I'm guessing they would use some sort of like correlation coefficient like R squared and stuff like that. Yeah. Yeah, that's good. Okay. Next one is similar. It's about bears. Oh, but notice this one is written what I call the normal way, or the way I like to see it. And this one about the bears is the weird way where they factored out the carrying capacity. But it says the population of bears in a newly established wildlife preserve is divided by that differential equation where T is measured in years. And then it has parts A, B, and C. So, okay, real quick. If you wanted to write this in the what I call the normal way, where this is the carrying capacity, then you would have to. Okay, let me point at some things before I over confuse you guys. To get from carrying capacity to a 1, all they did was factor out the carrying capacity. And so this number includes the carrying capacity in it. So what I mean is they factored out 3,000 to get from 3,000 to 1, or really actually they factored out a 100 out of both these to get from the carrying capacity to 1. See what I'm saying? Okay. I didn't know if I explained that very good. Felt like I didn't, but looks like you guys got it. So what I mean is this number is really 100 times the original K, because it has the 100 that they factored out to. Okay, so to get from this version to what I call the normal version, you would divide this one by 100 and multiply it with this one. So that would be 0.1234, 2 new zeros into this, 8. And then put that 100 into here. So distribute it back into this original. Okay, now was that super necessary for this question? No, I don't think so, because you can probably tell. Yeah, you don't have to write it this way, but if you like it in one particular way, you can always do that. All right, carrying capacity for bears in this wildlife preserve, what is it? Nice. Well, that's all they have room for.
No.
What is the bear population when it's growing fastest? Nice. And then rate of change, take that 50 and plug it in. Did you do it? Nice, y'all. 50 times 100 minus 50. And then, yeah, you get 0.2 bears per year, which is very few. But I guess for a wildlife preserve, maybe that makes sense. You can only get 1 bear every 5 years or something.
Why is there 0.08?
Oh, I'm wrong.
Wow.
Sorry. Good catch.
No, like mathematics, right?
Well, right. Okay, and then I think I'm kind of done. But just so you guys see what this looks like on the AP test, you're like, these must be too easy. These ones that Mr. Little wrote. But no, if you look through these, here's the 2019 one, here's the 2012, here's the 2018, here's the 2017. That's all the tests I have access to, and they're all pretty similar. So try those. I put the key on Schoology in the Calc BC like folder. And then let me say one weird thing that you guys aren't going to expect. But these practice problems would be like your homework problems. I recommend you do not do these right now so that you can come back later, like in a week or on Sunday or something, and see if you still remember how to do it. If you see it all in one day, you're going to forget it. I would say do these later.
The practice.
Boom. Oh yeah, song of the day. Let's check.